Hi, everybody. Thanks for joining us. Welcome to October's installment of BlueSciCon, Blue Marble Space Science Conversations. This is a podcast series that features the research ideas and philosophies of the members and friends of the Blue Marble Space Institute of Science. My name's Jacob. Thanks so much for joining us. You can learn more about our institute at bmsis.org, and you can listen to previous editions of our podcast at bmsis.org/podcast. We have Zach Adam, one of our research scientists, and also a postdoctoral fellow at Harvard, who is joining us to tell us about sort of a project he's thought about involving the origin of life and natural nuclear reactors, which is titled "This Temperature Oscillations Near Natural Nuclear Reactor Cores and the Potential for Prebiotic Oligomer Synthesis." I'm not a biologist, I can't even pronounce all these words. But Zach, thanks for joining us. I'm looking forward to hearing more about this idea.
Thanks for having me, Jacob. We're today going to talk about some very disparate comments or very disparate concepts that are going to take us on a journey from engineering through geology on our way to chemistry and biology. So we'll be covering a lot of different ideas, but I think just to kick it all off, it might seem kind of strange that we're talking about natural nuclear reactors and the origins of life. Like, what the heck would any of these things have to do with one another? And, where did this come from? And why is this even something that you would even tie together? I figured it would be the kind of most obvious place to start. And the basic idea is that energy, in all of its myriad forms that it can take, has within it, not all forms of energy are the same. We might remember the equation attributed to Einstein, E equals mc squared. And we know that energy is all around us and can do many wonderful things like power our electronics. We get energy from the sun. There's nuclear energy that can both be used for destructive means like atomic weapons or for peaceful means like power generation or moving submarines or even taking us into the far reaches of our outer solar system and powering some of the magnificent spacecraft that we have. But not all forms of energy are the same. And some forms of energy are much more useful than other forms for getting certain tasks done. We call this idea entropy, but it's something that we can relate to kind of at a visceral level. So if I tell you I'm gonna offer you one or the other, and I'm gonna offer you either a $100 bill or I'm going to offer you $100 in pennies, just bring in a wheelbarrow and just dump it out on the ground. I might ask you, like, which one would you rather take for yourself? And I'm sure there are lots of people out there who would love a wheelbarrow full of pennies or a truck full of pennies, but really this kind of gets at the idea of what entropy really is in terms of energy, because $100 in the form of a $100 bill is much easier to move around. It takes less effort to move from one place to the other. It has the same value. We can still obtain the same amount of goods with it, but inevitably we're going to have to, burn more calories either packing them into a backpack and taking it from store to store, or it just takes a lot more effort to use the value of $100 in pennies than it takes to use $100 in paper form. And that concept is what underlies entropy. Some forms of energy, even though they might have the same total amount of energy, can manifest different ways of turning from one energy into another, or one form of energy into another, and can create much more fascinating kind of intermediate states while converting from one form of energy to the other. Now, that's kind of a long introductory way to try to kind of wrap this concept of natural nuclear reactors, but this is exactly how I first turned toward nuclear reactors as a potential driver for interesting chemical reactions that could have possibly caused the origin of life on Earth, or maybe a primary driver for life on other planets with a source of like fissile elements on it. And the basic idea is that nuclear energy is like that $100 bill. It's a very compact form of energy which is why we use it for powering spacecraft to go to the outer reaches of our solar system, or why this massive nuclear submarines can guide themselves and be directed for years without replacing any of the fuel rods. Basically, in this entire vessel, only a couple of kilograms of fuel can power a multi-ton vessel for years at a time. And that's because nuclear energy has a very low entropy, which means it's a very ordered, very compact state of energy, and a process of converting that energy into either movement or electrical energy or heat can manifest itself in very interesting manipulable ways, and therefore has a lot of potential use. And that's one of the reasons when we look around, you might ask yourself, well, how many forms of low entropy energy are there available to us on the surface of the Earth now or in the past? And when you look at it, there really aren't a lot of very low entropy energy sources available to us. Sure, there's a ton of heat energy everywhere. Hydrothermal energy starts as chemical energy and then turns into heat energy and moves these massive cycling of seawater into sediments and out of these hydrothermal vents that we can explore and study on the seafloor. But really, let's try to kind of put it into perspective. The kind of range of energies that we talk about in chemistry are on the order of electron volts. So the amount of energy required to move an electron through a potential of 1 volt, something like that. When we look at X-rays, a kind of more powerful form of photons, those are on the order of, say, kiloelectron volts, meaning 1,000 electron volts. When we look at nuclear processes, the basic driving reactions that drive fission power, we're talking energy on the form of mega electron volts per reaction. So these are basically 1,000,000 times more powerful per reaction compared to a comparable redox reaction, which is like hydrogen and oxygen burning to create water or something like that. And these occur many, many times within a reactor to produce power in a kind of stable, sustainable way. And what happens is that we start with these individual reactions that occur on the scale of mega electron volts, millions of electron volts. And as the energy is dissipated, it steps down and creates a cascade of separate energy conversion reactions that can manifest some very unique kind of means of converting that energy that can then be driven into the formation of organic matter, and possibly may help to create the very complex forms of chemical products that we would need to start life. So that's basically what our talk and our discussion is going to be about today, is what's so special about nuclear reactors? How does the energy go from the splitting of an atom, like going back to the 50s and the peaceful uses of the atom and atomic energy, and how does it go from splitting of the atom to the creation of life? And why is this unique? Why are we looking at natural nuclear reactors specifically when we compare the various sources of energy that are available for driving prebiotic chemical reactions? We're going to cover all of that, hopefully, in this discussion.
All right, well, thanks, Zach. That's a really great introduction. So I guess maybe as a non-biologist, and I'm not really even a geologist, to my knowledge, there's one example of a natural nuclear reactor that we've discovered from Earth's history. Could you maybe tell us a little bit about that?
Sure. Yeah. So, and that's really what started this whole process of thinking about energy sources on the early Earth. So when you sit down and look at how fission occurs, usually we use uranium fuel, and everyone, especially in light of the recent deals that have been negotiated between the international powers and, say, Iran, which wants to have a peaceful nuclear program, everyone talks about enrichment, which is basically the ratio of the fissile form of uranium, uranium-235, compared to the bulk of uranium, which is uranium-238. Uranium-235 is the isotope that can undergo neutron-induced fission. And when you look at it, the amount of naturally occurring uranium-235 in a given sample is really low these days. It's on the order of about 0.7% by mass. But uranium-235 decays much more quickly than uranium-238. So when you go back in geologic time, and I mean, when I say geologic time, I mean on the scale of like hundreds of millions or billions of years, when our planet first formed, the enrichment level of the uranium that was found on our planet was on the order of about 21 to 22%. And this is an incredibly high enrichment level when it comes to generating just a stable nuclear chain reaction. That is, like, a fission occurs, some neutrons fly out from the fission event when the atom splits open, and then at least one of those fission, or one of those neutrons that flies out, hits another uranium atom and causes that to fission, and then one of those neutrons hits another atom, and so on and so forth. So there's this kind of sustained chain reaction going on. This was only theoretical. So we kind of figured out the basics of atomic energy throughout the early 20th century. And in the 1950s, a guy named Paul Kuroda postulated that back in time on the early Earth, you could have had these kind of natural, geologically occurring uranium-rich pockets of the Earth, and that if some water would have trickled in or something like that, there would be a sustained nuclear reaction. And sure enough, after everyone started mining global exploring and describing and mining naturally occurring uranium formations on the Earth around the planet in the 60s and 70s, they came across this deposit in Africa that had a slight deviation in the amount of fissile fuel that it had. Now, this set off all kinds of alarm bells everywhere, because someone thought, oh my God, someone is intercepting the fissile fuel between the mine and the plants in France, and they could be building, thousands of bombs with the kilograms and kilograms of uranium-235 is missing. And when they went back to the source, they kept systematically tracing, like, okay, it made it onto this plane, okay, it makes it to this processing plant, okay, it makes it to this processing plant, and they traced that missing amount all the way back to the source of the mine, which had some very weird hydrothermal properties when they looked more closely at all the minerals around it. And what they deduced was that this was actually a fully functioning, naturally occurring reactor, a fission reactor formed within a geologic deposit. Now, they found, after that, they subsequently found on the order of about, say, 15 or 16 different isolated, independent, kind of in the same pocket of geologic rocks. They found 15 or 16 different reactor cores that had all formed through the same process. And subsequently, they actually found another reactor core about 30 kilometers away that formed under similar circumstances. So yes, in terms of the geologic scale, we have this one example in rocks that are about 2 billion years old of reactors forming without human intervention. But it was a very widespread phenomenon even at that time. And presumably once you have the right conditions for it to occur at one point, it's probably going to be, perhaps not a macroscopic phenomenon covering the entire Earth, but it would definitely occur on a scale of, say, kilometers to tens of kilometers. It'd be a massive kind of massive geologic source of fission-driven energy driving subsurface circulation of water and recrystallization of minerals, and hopefully the production of organic material. Yeah.
So you talked about the Oklo site, which is, of course, now in eastern Gabon. I don't know what the geologic context was 2 billion years ago when this is actually happening. Mm-hmm. But you have to get the uranium concentrated fairly high levels in the rocks. Mm-hmm. Do we know how common those conditions were in the history of the Earth 2 billion years ago?
Well, for 2 billion years ago, yeah, we have some idea. We know that what happened 2 billion years ago at the Oklo site that we've just talked about, something unique kind of occurred. So uranium switches between being able to be dissolved in water and being precipitated out of water, depending on what the redox state is. If there's not a lot of oxygen around, it will dissolve in water and be transported, or it will precipitate out. If there's a little bit of oxygen, it will dissolve into water and it will not precipitate out. So what happened was that the water at the time was slightly oxidized and was therefore, it had a lot of uranium atoms kind of floating in solution. And then once those oxidized waters hit a reducing front created by organic matter that was already there from other organisms that had been buried, all of that uranium precipitated at that particular spot along a kind of reducing front. So that was the way that it got concentrated 2 billion years ago. And they think this was kind of a unique time in Earth's history where it's just after oxygen levels had begun rising to appreciable amounts in the atmosphere. So the entire planetary system was undergoing a transition from a previously reduced or neutral type of environment to an oxidized environment. And it's the juxtaposition between these different types of microenvironments that allowed massive amounts of uranium to be concentrated in a relatively localized volume. Earlier on in Earth's history, we don't think that this is a likely scenario for concentrating uranium. But given that the amount of uranium enrichment that would have been around in the earliest stages of the Earth's formation and differentiation of the surface environment, and that kind of initial cooling of the atmosphere, kind of geosphere surface environment, we think that it's possible that if there was a functioning type of crustal differentiation, weathering of crustal types of rocks by wind, rain, sleet, snow, and everything that we know around us now to drive conventional weathering processes of exposed portions of crusts and continents, you can actually just directly mechanically weather those source rocks and collect them as a result of tidal sorting. And what that means is that basically the uranium is present in these large crustal rocks. Rain, wind, and snow kind of break them down bit by bit. And because they're very heavy, because they fall on the lower parts of the periodic table, they tend to form minerals that are also heavy. And so as the little bits of the minerals get transported, just like all of the sands that you see when you go swim at the river or in a lake, all of those little bits of sand are getting transported from a source rock out to ultimately the ocean. And the moon at the time of the Earth's early formation would have been much closer than it is now. It's been kind of steadily receding away from us. And the moon would have been this huge factor driving incredible tidal variations, which means that as the tide kind of comes and goes along coastal margins, it can create these huge kind of beach environments where all these heavy minerals that tend to be transported through rivers can be sorted and driven up to the high tide marks of beaches, and they stay there because they only get deposited there during these large storm events or during these high tide portions of kind of tidal sorting. Tides come in, tides go out. The heavy stuff tends to get sorted and stays as a result at the high tide margins of the beach and are therefore semi-stable. And we've done some preliminary calculations. My first efforts in looking at this theory was to calculate, okay, if that's the only sorting mechanism that's around, and we have analog heavy mineral environments today that tend to sort heavy minerals into these types of environments, do those types of concentrations of heavy minerals match up with the amount required to reach fission criticality with the degree of enrichment that existed back then? And sure enough, we found that they are quite consistent with that amount.
So if you have an extensive weathering cycle, you can get this in other environments. Okay.
An extensive weathering cycle and basically tides on the order of what we have today, and presumably back at the Hadean, early Archean periods of time on the Earth, 4 billion years ago, with the proximity of the moon, you would have had much stronger tidal sorting of those minerals. Yes. Yeah.
So I like this idea. I think it's really cool. So I hear about hydrothermal vent origin theories and prebiotic soup origin theories. How does this fit into the mix of those? What are sort of the relative advantages of the natural nuclear reactor origin story?
So that gets to the title of the talk that I kind of threw out here for this. Like, why is it interesting for forming complex organics as opposed to any other kind of energy source that can form organic material, synthesize organic material? So basically you need, there are a couple of very interesting ways in which reactors function that end up producing this. They're not ideal, but they're very, very close to what we would imagine to be ideal kind of pressure and temperature variations that might help to synthesize long chains of reactive organic molecules. And then the kind of the key to all of this is to understand that reactors are not kind of an exterior form of energy, just pumping energy into the system. Like every day when we wake up, or night, or whenever it is that we wake up in the day, the sun rises in the sky, it irradiates the surface, and then it goes down on the other side. It's not something that whatever is on the surface of the Earth doesn't really change that dynamic. It's decoupled from the sunlight coming in. In some respects, we think hydrothermal vents function similarly. Like water from the sea floors is kind of pumped through these kind of different minerals. The water reacts with the minerals. The minerals undergo a redox reaction, which increases the temperature and releases a lot of different ions in the solution. They create hydrothermal vents. But this is really removed from any potential compounds that are produced down the line. So if hydrothermal vents do synthesize some basic organic compounds, it's going to occur whether those compounds are there or not. But reactors are different. Reactors have this kind of, they have this intrinsic aspect of them called feedback, where the way that the reactor works is contingent upon the materials that are put into it. And the strongest regulating factor of the way reactors function is water. When we talked about how when the atom splits open, neutrons fly out, but these neutrons flying out of this super energetic reaction do not necessarily bombard other fuel atoms without first bumping into a bunch of water molecules or something of a lighter atomic mass. So the water that's present within a reactor regulates the rate at which these fission reactions are occurring. If you have water in the reactor, it's going to slow down those neutrons, it's going to thermalize them, slow enough that they interact with other fissile fuel atoms, and the chain reaction keeps taking place. If you remove water from that system, in general, you're not going to have a natural nuclear reactor. What happens is that those neutrons that are flying out from the broken atoms just go flying straight out of the reactor core and don't interact with anything at all.
So we couldn't think about this setting on like a beach on Titan, for example.
No, it's actually, you need, there's some interesting dynamics because then you get into phase changes and what's going on. So you could have theoretically an ice reactor or something like that, but then you would increase the temperature so much it would reach criticality and keep pumping out so much energy that at some point it would turn into water and then at some point vapor and then be driven away. So there's this kind of, it quickly becomes a very complicated system to think about, which is one of the reasons I was drawn to it. But at the heart of it, you need liquid water to moderate the neutrons. And once you pass over the boiling point, the water in the core turns to steam, and you have these big pockets where neutrons are not getting slowed down. So the reactor kind of shuts down a little bit, or it's kind of teetering on the edge of operating, being critical and subcritical. And it's self-regulated by the fact that once steam forms, the temperature, the power production drops, and the reactor is no longer functioning in a critical state. Now, why is this important? What this means is that the temperatures in the reactor are inherently governed by the boiling temperature of whatever is moderating the neutrons. So if you have water there, the peak temperature is going to be, at the surface under current pressures is going to be 100 degrees Celsius. If it's buried a couple of meters beneath the surface, it's going to be about maybe 150 to 200. If it's buried deeply beneath the surface, it's going to be about 300 degrees Celsius. It's an inherently governed process. And the catch is that if you are generating organic compounds, you're also going to change that regulation temperature. Organic compounds tend to have a lot of hydrogen making up the molecules. And as long as there's hydrogen somewhere in the system, that's going to tend to moderate the neutrons fairly well. So what's going on is that if you can start out at the beginning of a reactor operation, some peak temperatures reached, and if a little bit of organic compounds are, like say monomers, just simple organic compounds are created by the radiation that's being given off by the reactor, those compounds are a slightly higher mass. They're going to hang around near the reactor a little bit more easily than water is. So the next time the reactor operates, you have a slightly increased amount of organic matter that's more likely to interact with the radiation being given off by the reactor. So it creates a little bit more organic compounds. The next time the reactor functions, you might have a sizable fraction of organic matter that's around and being bombarded by the radiation. And at the same time, the organic compounds will tend to increase the upper limit of the formation of these void spaces within the reactor that are going to moderate the neutrons. So you're going to actually be incrementally increasing the peak operating temperature of the reactor core as you accumulate more organic matter in the system. And what's interesting about the Oklo comparison is that so much organic material became concentrated in the core that it actually stabilized the physical configuration of these uraninite grains that were in the core. So the core became stabilized as a result of hydrothermally and radiolytically interacting with the organic matter that happened to be present around the reactor core, thus greatly extending the lifetime of the reactor and increasing the probability that it would be a long-lived energy dissipation phenomena that exists long enough to be preserved in the rock record, for example. So all of this taken together, this is fundamentally one of the reasons why I'm very interested in natural nuclear reactors, because if you govern the peak temperature of operation at about the boiling point, and it's periodically becoming active and non-active and active and non-active, you start to create a temperature profile that reaches a high temperature, falls down a little bit, and has these kind of oscillating phenomenon of peak temperature and then normal temperature, peak temperature, normal temperature, peak temperature, normal temperature. And this creates some very interesting kind of reactions that are called condensation reactions. So basically, one of the outstanding problems in prebiotic chemistry is how do we form these really long, delicate chains of molecules when the way that each of these little pieces of the chains connect to each other relies on there not being water around. You need to actually remove water from these molecular systems and connect them in these chains by either having a chemical catalyst that goes in and removes the water and keeps them connected to each other, or you can drive it through oscillating from a liquid state to, say, a steam state, or a liquid state to a vapor state. And it's that phase transition and switching periodically from a wet condition to a drying condition that can help to form these very delicate bonds that subsequently add chemical compounds to one another. So there's kind of, when you look at these long complex chains of oligomers or polymers, which is just individual mers all connected to one another, there are basically 2 or 3 different types of energy inherent in that system. There's the energy that formed the chains themselves, the pieces of the chain, and then there's the kind of energy that allows those pieces of the chain to be added to one another. And so in an energy system, you're looking for an overlapping, 2 or 3 overlapping types of energy that both allow the chains to be created and then the pieces of the chain to be linked together. And that's exactly what nuclear reactors kind of resemble in the way that they function. And it's kind of an emergent property of the way that reactors are governed by neutron moderation.
And can they like easily detach from the substrate once they're formed?
Can the pieces of the chain detach from each other or from the minerals? Like, what do you mean by substrate?
From they require some kind of catalyst to form on, right?
No, in this sense, that's one of the things, that's one of the reasons why I really want to investigate this phenomenon. It's not clear whether if you drive the formation of the chain links, the MERS, and you provide this kind of variable heating, cooling, and wetting, drying cycle, you're not actually driving it with a catalyst. You're not driving it on a surface that they need to detach from. You're driving it in the bulk chemistry of the volume around the reactor itself. So there have been previous experiments that use catalytic either mineral surfaces or ions in solution to try to basically bring these different pieces of the chain together on the surface, force them to kind of link together, but then you have to detach them from the surface. In this case, it's kind of a bulk volumetric phenomenon in the region surrounding the core itself.
Okay, I get it. So it's not a closed system, and then so that water with those newly formed oligomers can then infiltrate away via cracks to some other environments.
They're basically formed in the volumes that are like it's kind of, there's a kind of a Goldilocks problem of its own when you deal with reactors. If you're too close to the reactor, you're getting shot all to heck with all of this radiation that's being given off, alpha, beta, and gamma particles. But if you're far enough away from the reactor, there's a lot of shielding that gets rid of all those ions, and you're left only with the kind of neutral forms of radiation, so gamma rays and neutrons. But the question is whether that variable temperature oscillation that's inherent to the governed core of the reactor propagates outward far enough that you still are you have the radiation driving the synthesis of the compounds, and then you have this temperature oscillation that might or might not drive the formation of complex polymers. And so that's the open question that we really, really want to investigate with some kind of laboratory setup.
Sorry, I'm trying to mute in and out because this baby's screaming. So. But, can you estimate what the dose rate is as a function of distance from the surface of one of these?
Yeah, I've got some figures here. It's kind of difficult to convey in podcast format, and maybe I can touch base with you afterward. But
yeah, that'd be great.
But basically, there's a couple of advantages in the way the dose rate itself is one of the inherent advantages of the system. So when people think of reactors, they think they're these, monsters of energy dissipation. Like if you get anywhere close to the reactor, you're just going to get vaporized instantly, and your face will melt like in Indiana Jones or something like that. But natural nuclear reactors are like a gentle giant of energy dissipation. So they give off a lot of energy, but they give off that energy over hundreds or thousands of years. In fact, the reactors at Oklo were thought to operate continuously on the scale of megawatt or of a few kilowatts, kilowatts to megawatts for 10 to the fifth, almost a million years. So it depends on a lot of factors for what the dose rate is going to be as a function of distance. It depends on what the enrichment level was. We have a pretty good idea what that was. It depends on exactly how much is concentrated within the reactor core, which gets back to Michael's question about, do we know how much and how it was concentrated? But in general, I think the fact that it's governed by the inherent boiling temperature of the moderating fluid might help to set some bounds on exactly how much the dose rate would vary with distance, because you're still inherently set by that boiling temperature. And this has been estimated for the Oklo reactors. And if you look at it, it's basically equivalent to, if you look at, say, a cobalt-60 radiation source that's used at, say, at NASA Goddard for its radiation effects facility, or at Tokyo Tech, they also have one there. If you were to get really close to that source, in about a month, you would get the amount of radiation that would correspond to about maybe a year or 2 years of continuous reactor functionality. So that's what's interesting about the kind of next phase is that conducting these experiments in a lab can reduce what we think is a geologically kind of scaled phenomenon down to something that we can observe in the lab, hopefully, on laboratory types of scales of observation.
So you're talking like megagray per year.
Yeah, that sounds about right. I think there was a really good a paper that was put out by Dondi et al. It was an Italian group, in 2011, and they did, I think it was on the order of kilogray per hour, and then they bombarded it for, you know, a month. So that's on the order of a megagray, yeah. So, yeah, and they actually, and so that's the other part of this interesting framework, is that what they found as a result of gamma radiation were purines and pyrimidines, which I'm a geologist, so I don't understand chemistry at all. But when I Wikipedia purines and pyrimidines, I see that those are the two classes of compounds that form the respective parts of DNA strands that match up with each other. So the GC pairs and AT pair, whatever the other two is, it's a purine and a pyrimidine attached to a sugar, attached to a phosphate. And those form the different strands that match up to one another in DNA. So if we've got this kind of process that tends to produce purines and pyrimidines, and we have these really interesting temperature variations that more or less kind of resemble the types of temperature profiles that we use in polymerase chain reaction devices that are used to engineer and synthesize and rapidly replicate DNA and RNA strands in the lab, then the only things that we're left to look for are sugar and phosphates. So the last part of the question, the other reason why I'm really interested in natural nuclear reactors is because heavy minerals tend to have a lot of phosphates with them. So, and there was a great study done in the 70s, and I don't know why it hasn't received more attention. I hope it's not a spurious type of finding, but there was a group that found that apatite, which is one of the most common phosphate minerals that also tends to occur in association with heavy mineral placer beaches, on the order of a couple of percent. Usually it's not even included in the mineral description because it's only 1 or 2%. But apatite tends to be found in heavy mineral placer beach deposits. And apatite, the surface chemistry, kind of like what Sanjoy was talking about, apatite can catalyze the phosphorylation of organic compounds. And I believe it does tend to catalyze the type of kind of configuration that the phosphate has with the organic compounds that are found in life. So again, this work hasn't really been followed up because it was not really seen in what type of environment would you have a lot of apatite sitting around with a lot of monomer compounds with these kind of temperature variation. It seemed like too much of a stretch to say that, okay, apatite's just going to sit there and create a bunch of phosphorylated compounds. But within the framework of this kind of geological setting, it's not only possible, it's probable, because of the way these minerals tend to be found with one another. So that's the other part of the experimentation that I think would be really interesting. Can we couple organic compound, carbon compound synthesis with reactive phosphorylated compound synthesis? If we can get those in the same volume at the same time and interacting with one another, as Carl Weathers in Arrested Development said, you've got yourself a stew, baby. Yeah, some good Arrested Development jokes out there.
So, are you planning on setting up some of these experiments then?
I hope to. My current job title is technically micropaleontologist. So I got started with this work a long time ago. I'm seeking out sources of funding, and I know that there are people who are interested in this particular type of theory and setting, and I've been talking with potential collaborators, specifically at Tokyo Institute of Technology, ELSI. It's a fantastic group that's very interested in focusing a lot of attention to origins of life problems. So, you know, even if I don't get funding or anything to do the work myself, nothing would make me happier than for someone else to take the idea and run with it with the resources that they have as well. So I see a couple of different experiments that are very easily possible. Just using conventional irradiation sources that are available for other purposes and using them for these types of reactions, like the Dondi et al. Group did in 2011, I think is a very feasible kind of short scale test of these kind of concepts. Trying to couple carbon with phosphorus chemistry is obviously kind of a low-hanging fruit objective that makes sense. Coupling organic compound synthesis through radiolysis with a variable temperature profile that you would expect in the vicinity of natural nuclear reactors makes sense as another kind of low-hanging fruit of experimentation. And the good news is I don't think it would require a lot of inquiry to find out whether this makes sense or whether it's all just a bunch of, very speculative, very interesting, potentially insightful, but highly theoretical kind of theory. And the number one key right now is to try to make that transition from potentially interesting, potentially insightful theory to a laboratory setup that actually generates a lot of oligomeric or polymeric compounds with the kind of chemistry that is associated with life.
All right, well, this is really exciting. If I can ask one final speculative question.
Sure.
How would you tie this in with exoplanets and the search for life? I mean, is this just planets that are more Earth-like and might have a similar geologic history to Earth, may have natural nuclear reactors? Is there any other sorts of environments that might be more conducive to this type of process than Earth?
Yeah, and that's one of the coolest areas to think about, in my opinion, is how commonplace is this phenomenon? Like, is it just Earth? Is it some weird aspect of Earth was this kind of one-off kind of planet that is likely to have nuclear reactors as part of its geologic history? Or is it something that could possibly be endemic to a lot of different planets that we are finding around all of these other stars? And the promising kind of aspect of it is that I don't think this is particularly unique to Earth at all. The enrichment levels, as I said, when Earth formed is, depending on the specific amount, would have been between 21 and 24% of uranium-235 enrichment. That is a very high enrichment level. You can generally anticipate reactors forming down to enrichment concentrations of about 2 to 3%, maybe 4%. Under geologically plausible scenarios. In fact, the example of the natural nuclear reactor that we have from our own Earth history occurred right at the end of when we think it's theoretically possible for reactors to have occurred. So they could have been a more widespread, common geologic phenomenon earlier in Earth's history. We just don't have much of a rock record to piece it together. So that's basically 2.5 billion years worth of Earth's 4.5 plus billion year history where these things could have formed. There's no particular reason to think that Earth has more or less fissile elements than any other rocky planet. In fact, there was a paper that came out, I think last year, that speculated that the Earth's complement of fissile isotopes is actually anomalously low and may have been blown off into space during the moon forming impact. I can't recall the specific author, but you can find it relatively easily with a Google search. So it actually might be the case that Earth shouldn't have been forming natural nuclear reactors, but did, despite the fact of the moon forming impact, vaporizing and obliterating the protocrustal surface of the Earth and sending it flying off into space where it could never again be seen to drive any interesting organic compound reactions.
But would that mean that the moon may have also some of these reactors?
I think the moon is thought.
Well, I guess you don't have the water, so.
You don't have the water.
There's not enough of a weathering cycle.
Yeah, and not much of a weathering cycle. But on the other hand, you don't necessarily need to. We're using the beach kind of model to look at life because it has everything we need. It has access to the atmosphere as a gaseous component of reactants. It has water. It has everything that we're interested in for life. But that doesn't mean that there couldn't have been the source rocks before pre-weathering moved the uranium minerals around. You could have had actually these kind of buried reactors that were near the crustal surface environment where pore fluids kind of go through the crust all the time. And you could have what are called pegmatites, which are thought to be the source rocks for natural nuclear reactors. They're kind of granitic type of rock with these giant crystals. They're basically formed under conventional magma cooling circumstances. There's nothing unique about them. But they also tend to occur in these kind of weak points of magma pockets. So water can very easily flow through these types of areas. So you could imagine there being reactors buried, kilometers beneath the surface of the Earth. And as pore waters flowed into the system, you have a completely subsurface cycling of pore fluids through pegmatites that reach criticality, bump up the temperature really, really quickly, and possibly very high temperatures because the boiling temperature of water under pressure is so much higher that it drives the water out of the system. It periodically cools, the water comes back in, and the cycle repeats itself underneath the surface of the Earth without a beach component. We're using the beach setting because it's the most accessible, and it kind of makes sense from a narrative storyline of trying to design experiments, but there's no reason that they could not have also occurred underneath the surface of the crust, relatively close to the surface. So in terms of ubiquity, I think as long as you have, a rocky planet roughly the size of the Earth, forming under conditions like kind of in terms of the time duration from the supernova that produced all of the matter around us to the formation of a planetary system, I don't think there's anything particularly unique about the Earth system as we currently understand it. As long as you have any rocky planet forming within a couple of billion years of a supernova, it's going to have a relatively high fissile element component of its crust. And as long as you have water percolating into the system and standard magnetic processes as we understand it, you're going to have natural nuclear reactors. So the exciting answer, I realize I covered a lot in that answer, but I don't think there's anything particularly unique about the Earth. And I would guess that this would be a fairly common component of any young planet found around any kind of typical star system. So it could be going on all over the place.
I think this is really neat to think about, and definitely look forward to hearing how these ideas and hopefully experiments start to produce some results. Thanks again for chatting with us, Zach. This has been a lot of fun. Listeners, thanks for tuning in. This has been BlueSciCon. You can check us out online again at bmsis.org/podcast. We will see you again next month. Thanks so much.